Next up is Gernot Heißel, who is going to tell us about nuclear cluster, dark matter, or both.
Okay, thank you very much, and thanks a lot also for the organizers for the opportunity to present. So I'm going to present constraints on distributed matter in the innermost galactic center, and I will already say, so in contrast to the talk before, when I say innermost, I mean the innermost 0.01 parsec, so it's 10 milliparsec. And I will summarize work done under the affiliations of Paris Observatory, the Gravity Collaboration, and now at the European Space Agency in the Advanced Concepts team. And let me start first with this paper here from Paris Observatory. First, some brief background. So what are we actually looking at? So I already said galactic center, and we are really looking at the two-body problem, extreme mass ratio two-body problem, the massive black hole Sagittarius A star, plus one single star. And in particular, we're looking at the innermost, which we can track very well, which is the star S2. So if we would model that, so first naively Newtonian style, we have here the simple two-body problem. So we would have a Kepler ellipse, bringing in relativity, and we are here at a radii where we can comfortably use the post-Newtonian expansion. We get here an additional term, and the net effect over many orbits would be that the ellipse is now prograde precessing. And then we are asking the question, okay, maybe there is more stuff we just don't see. And what could that be? There could be something which I would call ordinary dark matter, or you might call it boring dark matter. So it could be just a cluster of faint stars or stellar remnants, so black holes, for example. Or it could be dark matter in the sense of which we're talking here at this conference, so in the sense of yet undiscovered particles or fields. Or, and that's actually often forgotten in the modeling, it could be both, right? I mean, it's not unreasonable to assume that there are more stars which we don't see and dark matter in the sense of, for example, cold dark matter. Yeah, and the net effect of if you have distributed matter onto a stellar orbit is over many orbits, it accumulates again a precession, however, it goes retrograde, so it counters the Schwarzschild precession. But in addition to these effects which accumulate over many orbits, depending on the dark matter you have, you also get effects which within one orbit, so depending on which type of dark matter you have a different distribution, and you would see each single ellipse here having a slightly different shape. So what did we do in this paper? So we coded a model based on these equations of motion, and we let the acceleration coming in from the distributed matter be generated by two density distributions here. And the ones we've chosen here, they are motivated by ordinary matter, so they model the relaxed states of stellar clusters or nuclear stellar clusters, but also the Barkal-Wolf cusp here, so that would be the nuclear cluster, also has a profile which fits actual dark matter models. So for example, if you think on cold dark matter spikes as proposed by Gondolo and Silk, they have also a power law distribution like that with exponents in the range where this falls in. So it's in this sense, it's also an example of cold dark matter. And what did we do? We performed two kinds of analysis. First, we plotted model orbits and compared them with and without dark matter. And then we produced some mock data and see what can we learn from fitting the model to mock data. And the key result of this paper is summarized in those two plots. So this is a plot. We have three models here. The one in blue has no distributed matter, so it's a pure two-body problem. The other two, they have distributed matter of the two different profiles which I've showed you before. And we are looking here at the argument of pericenter versus true anomaly, so versus the position of the star within the orbit, and the true anomaly marks the point of the pericenter. So if this curve is increasing, you have at the moment a prograde precession. If it's decreasing, you have it retrograde. And what we can see is that those models, they coincide basically up until this point. So up until here, you don't feel the dark matter, basically not at all. I mean, there will be tiny differences, but on first sight, they overlap pretty well. And this shaded region here is then actually where the dark matter starts to have a difference, and the effect then basically switches off again at a certain true anomaly where those curves again go parallel. And if you translate this now into how, astrometrically on the orbit on the sky, you see that the relativistic precession, which drives the prograde one here, happens basically exclusively on the pericenter half, whereas the dark matter precession happens exclusively on the apocenter half. And it is intuitive that the dark matter effect, as we already heard in the talk by Dikong, is strongest the further you are away from the black hole, because then you have a strong gravitational pull from the maximal amount of mass. But what came a bit of a surprise is that it's really such a clear-cut separation. And this, of course, not in full generality. So this is basically, when you look at it in more detail, it's a consequence of that you're looking at the quite elliptic orbit. So it's not magic, but you wouldn't think at it in first glance. If you would have a circular orbit, obviously, you don't see that. Yeah, so, and this was important for us. So I'm also in the gravity collaboration for our observations, because up until 2020, we had data with our most sensitive instrument, the gravity instrument, precisely on this part of the orbit. And so we learned if we continue, we have to continue observe, giving the star S2 a priority in our observations if we also want to make stronger constraints on dark matter in the galactic center. Yeah, and then we got a few other results out of that, of our analysis. We don't have plots now, so we learned we need at least one orbit of data to get good constraints. Given one orbit of data, it actually turns out that the pericenter half appears to be the stronger constraining one component. So you need both components, but the data on the pericenter half gives the stronger constraints, which it's again a counterintuitive result. And in the mock data analysis, we estimated how does, in the years ahead, how will the constraints improve. So up until 2026, we will have the next apocenter passage. In 2023, we will have one full orbit of gravity data on the star S2. And so these are the results in 2020. It was at about 4,300 solar masses within the orbit, so within the full apocenter, a ball of apocenter radius. And with one full orbit, we will bring this down to about 1,000 solar masses. So this was a theoretical and mock data study. So then the second paper I will present is now looking at it with actually real observational data. And as you probably know, so in 2020, the Schwarzschild precession has been measured by the gravity collaboration. And since then, so with 1 year more of data, because one year we lost because of COVID, we were looking how can we improve the constraints, and we didn't only have more data for S2 then, but also data for other stars. So in particular for 4 stars, we had now also gravity data, and we refined a bit our analysis, and so how we could improve constraints. Yeah, so what is the refinement of the analysis? So we allowed ourselves to throw out some old data from less sensitive instruments near the pericenter, where we now also had gravity data, because this is less susceptible to source confusion. And we did an update on the fixing of the rest frame of the older instrument, because so this is something I don't know much about, but I understand as much. If you observe over a long period, then it can be that the rest frame of your instrument is rotating, and that of course can simulate something like a precession effect. So you need to be very sure that you take that into account into your modeling properly, not that you think you measured something which actually didn't happen. So this also has been refined, and then we fitted again a model based on these equations and tried to constrain those two terms here, the relativistic precession and the dark matter precession. And what is the result? So we improved the measurement on the Schwarzschild precession from 5 sigma, from a 5 sigma rejection of Newtonian physics to a 7 sigma rejection of Newtonian physics. And we improved the dark mass constraints from 4,300 solar masses to 3,500 solar masses within the apocenter radius of S2. And so when I saw that, I was quite happy, because the paper before gave the theoretical prediction, and that would be between 2020 and 2026, and the constraint really falls in here. So that means at least we didn't screw up completely on the theoretical paper. And so these plots are to give an impression of that the data really follows the relativistic orbit and not the Keplerian. So this is a residual plot, relativistic orbit minus Keplerian. So if you would be in Newtonian physics, the data points should follow this line here. Yep, thank you. Yeah, so so far so good. So far, I talked about approaches where we assume a certain density distribution. So in some sense, the constraints which we have this way, they are not fully general, right? So they only hold if the matter is distributed in the way we assume. And in particular, the shape is also dependent on the nature of the dark matter. Depending on the model, you will have a different distribution. So if you really want to learn not only how much matter is there, but what kind of matter is there, you would have to go through a very tedious comparison of a zoo of candidate models of dark matter. And as I emphasized before, it's not excluded that they might not be superposed, right? For example, background star cluster plus particle dark matter, something like that. So model comparison is something very difficult. And so in my latest project, we looked at together, so the main actor here actually was an intern, so I gave him this problem. And we were looking, can we find an unbiased approach? Can we try to first find the distribution in a model fit and then afterwards worry about what it is? And for this, we cooked up a model kind of like onion shell model of dark matter. So we construct dark matter distributions via a series of concentric mass shells. Each shell is radially Bell distributed. That means if you look at the enclosed mass at a certain radius, if you assume spherical symmetry, you will see smoothed out step increases. Here they are quite coarse for demonstration. For the actual analysis, then we smooth them out that we can approximate popular dark matter curves much better. And so the parameters of those models are the masses of those shells. So in other words, they are the increments of those steps. And what did we do then? So we produced mock data, and then we tried to fit this data with the model, and so checked first, can it adapt to all these different kinds of distributions? And can we, with current instruments, is there a chance that we really can fit the shape and not assume it a priori? So what are the results? So first we had a proof of concept. We produced mock data without error bars. So this is of course not the real world, but it was nice to see, okay, our fits really end up at the ground truths which produce the data. So proof of concept in this sense. And then we introduced measurement errors on our mock data. And first we were quite small with the errors. So this is 1/10 of the current instrument precision which we have. So it's much smaller than we actually can measure. And we saw that the problem becomes strongly non-convex. So depending on which initial conditions we started for the fit, we ended up in slightly different places. However, what was nice to see, at least statistically, the reconstructions cluster around the proper ground truth model. However, still with quite small error bars. If you then increase to the current measurement sensitivity, and just to give you an impression, so the gravity instrument can track S2 with 50 microarc seconds. That's the angle you would see a grapefruit on the moon. But unfortunately, in this case, our model with one orbit of data, 3,000 observations, you can see trends, but it is not good enough that you could distinguish, okay, it is either this profile or that profile. We ramped them up further, so we also checked, okay, same number of observations, but 10 orbits. And an interesting thing we saw here is, well, we do get better trends for some of them, but so this green model here, the Zhao model, unfortunately was not found. But in all cases, what was estimated fairly well, I mean, not very good, but we ended up here in the right amount of total enclosed matter within the upper center radius. And this is nice to see, because this is due to that we have here 10 orbits of data. So if you collect more orbits of data, you will get quite good constraints, even with with large error bars on the data, on the total amount of distributed mass. But you may still not be sensitive to the actual shape of the distribution. This is because we see the secular effect. We see the precession, but we don't see how each ellipse in this precession is different from another. We have more plots. I don't have all here. But if you would ramp up now more observations, of course, you would get more and more accurate here. But the bottom line is with current instrument precision, so we have to think one orbit is 16 years, 10 orbits is 160 years. With current instrument precision, it's hopeless to really distinguish. And our key claim is that this is not a detriment of our model, but this shows that it's not possible. Unfortunately, we have to assume, we have to put in physical assumptions of the dark matter distribution. We cannot, unfortunately, at the moment, with current instruments, have an unbiased approach. Okay. Thank you very much.
We have time for one very quick question. Does anybody have one? Right here.
Yeah. So what about using different orbits, so different objects with different also eccentricity? So that would probably probe different places.
Yes, so this is true. You could, of course, you could bring in more data if you have more stars, for example. And this may be a way to improve it, of course. So this is the innermost star, which we can track well, and it already has a 16-year orbit, right? The further you go out, the larger you will have the period. So to get really good constraints on the orbit, you will have to wait a very long time. But I mean, it's true, especially once the ELT goes live, we have a much wider field of view and can in one picture track many more stars. So this is a hope that it may improve the situation for such a kind of model.
Let's thank Joe once again.